So I want to talk to you guys today about some properties of the definite integral. Last time we talked about Riemann sums, and so we use those to approximate the area underneath the curve. Well, today we're going to look at how we can use the antiderivative evaluated at a function or evaluated over an interval, and this will actually give us the exact value of the area under the curve. So basically, what happens is if we look at the limit as our delta x or our change in x goes to 0 of like our LRAM or our RRAM or whatever it is, then this is going to give us the exact area under the curve. So, and this limit actually is equal to your integral. So we have that this limit right here, as delta x goes to 0, is going to be the integral of our function. And then this delta x we call basically dx. And what's going to happen here is that this is going to be those infinitesimally tiny rectangles that we're using to approximate the area, and we're able to do this with the antiderivative. Some really cool. I wanted to show you guys some properties of the definite integral. So we're going to be looking at specific areas and not indefinite integrals. Um, so here are a few that I wanted to show you guys. Here we want to look at negative area, which you guys probably think is a pretty strange idea. But seeing as, for calculating the area of these infinitesimally tiny rectangles, then, the height of, say, this rectangle right here, if you can see where I'm shading, is going to be negative. And whenever you calculate the area, it's going to give you negative area. So you have to pay really close attention whenever you're evaluating definite integrals or maybe looking at a picture, that you are making sure that your negative area is negative and your positive area is positive. Another property I wanted to remind you guys about was that if you integrate a function from one constant to the same constant, then this is always going to be 0 because you don't have any width to your rectangle. Here's a few others. If you have, say you have the integral from a to c, and you know that you have a and then b and then c, then you can take and you can either split up your integral or combine it together. You can go backwards or forwards. And you can say that the integral from a to c, as you see right there, of f of x dx is just going to be equal to the integral from a to b f of x dx plus the integral from b to c f of x dx. Sometimes we use this property when we're interested in, say, like the total distance traveled by a particle, and we have some negative rates and some positive rates. Then you would take and you would split your integral up so that you could make all the negatives positive. Another property is what happens whenever you switch your limits of integration. So if you flip your limits of integration, then what's going to happen is that you're basically traveling backwards as you accumulate the area, and so all those delta x's are going to be negative. And so you are going to just put a negative sign on the outside if you flip your limits. Another property which you guys probably know is that you can evaluate integrals separately, which you have already done before, but you maybe just didn't think about it that way. If you, say, are trying to evaluate the integral of x squared plus 2x dx, then whenever you evaluate this improper integral, then you're basically just going to evaluate each piece, although you may not rewrite it and actually do it that way. Also, if you take like this piece right here where you have this 2, you're just going to pull that constant out front. Although it kind of already happens, you may not, automatically do it that way. So I just wanted to practice a few definite integral problems with you, show you a few tricks, and then that's basically it. So here, instead of see what I have. Well, no, I'll do this. So here we're given some information about two functions. One function is f of x, and we know that the definite integral from 0 to 5 is going to be 5. And then we have another function, g of x, and we know that its definite integral from 0 to 5 is going to be 12. And then we want to answer a few questions. So here's a pretty simple one. So we have the integral from 0 to 5 of f of x plus g of x. So I can use that linearity property and rewrite this as integral from 0 to 5 f of x dx plus the integral from 0 to 5 g of x dx. And then each one of these I know are already given to me. This one, and I value it's going to be 5, and then that one's going to be 12, and so I end up with 17. So let's take a look at 44. All right, so here I have the integral from 0 to 5, and I'm going to rewrite this. I'm going to take, and I'm going to split up, use that property of linearity. I'm going to put the 2 on the outside. So this would be 2 f of x dx minus 1/3 the integral from 0 to 5 g of x dx. And then I'm just going to plug in. So this would be 2 times 5 minus 1/3 times 12. So that's going to be 10 minus 4, so that would be 6. Here on 45, I have the integral from 5 to 0, so I've just reversed those limits of integration. So this is just going to be negative the integral from 0 to 5 g of x dx. So this would just be negative 12. The last one is a little trickier because I have a feeling some of you guys would forget to do this. But let me erase all this stuff right here. But here, I'm going to go ahead and use that property and split this up. X dx. And this, 0 to 5 f of x dx, is just 5. But on this one, I actually have to, use the power rule and integrate this. So the integral of x is 1/2 x squared. And I'm going to evaluate that from 0 to 5. And so this is going to give me 5 minus, and this is going to be 1/2 times 5 squared minus 1/2 times 0 squared. And so 5 squared is 25, so 1/2 of that would be 12.5. 5 minus 12.5 would be negative 7.5. So here's just some neat ways you can manipulate and evaluate integrals. And so let's talk about the last thing, which is the first fundamental theorem of calculus. And we're going to work with this more next time. But it really just kind of defines the definite integral as the antiderivative of your function little f evaluated at the upper limit minus the antiderivative of f, a value of little f evaluated at the lower limit. So it's basically just defining what the definite integral does for you. There's a lot of neat ways you can manipulate this, but I just wanted to use it just kind of to work some basic definite integral problems. So let's take a look at some of these questions that I have here. All right, so anytime I just have this single function and I have an x in the denominator, I would automatically rewrite this with negative exponents. So I'm going to go ahead and pull the 8 out front, and I'm going to write this as x to the negative third dx. And so this is going to be 8, and then I'm going to do 1 over negative 3 plus 1, x to the negative 3 plus 1, evaluated, oh, I forgot this, from 1/2 to 1. And so now I'd simplify just a little bit. This is going to be 1 over negative 2. So that's going to make this a negative 4, x to the negative 2, evaluated from 1/2 to 1. And so that's going to give me negative 4 times 1 to the negative 2 minus 1/2 to the negative 2. So this is going to be 1 minus 4. So that's going to be negative 3. So negative 4 times negative 3 would be positive 12. That's pretty simple. Okay, let's try 25. All right, here I have the integral from pi over 4 to 3 pi over 4 of sine theta d theta. So the integral of sine The integral of cosine is would be sine because the derivative of sine is cosine. But the integral of sine is, or the antiderivative of sine is going to be negative cosine. So this is negative cosine theta evaluated from pi over 4 to 3 pi over 4. And so then I'm just going to plug in. So negative cosine of 3 pi over 4 minus negative cosine of pi over 4. Cosine of 3 pi over 4 is going to be negative root 2 over 2, so this is going to be positive root 2 over 2 plus, and then cosine of pi over 4 is going to be root 2 over 2. So this becomes then 2 root 2 over 2 over 2, which is just root 2. Okay, on the last one, this becomes a little trickier because I have an exponential function this time. But now I'm going to integrate from negative 2 to 0 of 3x minus 9e to the 3x. So I'm going to split this up. I'm going to do the integral from negative 2 to 0 of x dx minus 9 times the integral from negative 2 to 0 e to the 3x dx. So when I integrate x, it's just 1/2 x squared, so this becomes 3/2 x squared minus. Now this e to the 3x is a little trickier because I have a linear function as my inner function or my exponent. And so whenever I were to differentiate e to the 3x, I would have to use the chain rule and multiply it by 3. So to undo that, I'm going to have to divide by 3. So this is going to be 1/3 times 9 times e to the 3x. And then I'm going to evaluate this from negative 2 to 0. So this is going to give me 3/2 0 squared minus 3e to the 0. It's one piece minus 3/2 negative 2 squared minus 3e to the negative 6. Let's see what happens here. That's going to be 0. This is going to be negative 3, so you have negative 3 minus. Negative 2 squared is going to be 4, so this is going to be 6. And then the minus minus will become plus 3e to the negative 6. So I end up with, I hope I did that correctly, negative 9 plus 3e to the negative 6, and that'd be my final answer. So just make sure that you remember that it's always going to be the antiderivative evaluated at the upper limit minus the antiderivative evaluated at the lower limits. Make sure when you have multiple pieces to your integral like I do here that you are going to distribute. And I think that's basically it. All right, I'll see you soon.